When Richard Feynman talked about mass as a measurable property rather than a philosophical mystery, he was deliberately pushing back against a deep human habit, the desire to define things by meaning before understanding them by behavior. From childhood, people ask questions like, "What is mass really?" as if nature were hiding a secret definition that, once revealed, would suddenly make everything clear. Feynman's approach was radically different. He argued that in physics, the most honest and powerful understanding begins not with words but with experiments. Mass, in this sense, is not something we first explain and then measure. It is something we measure first, and only later try to describe. In everyday life, people think they know what mass is. They associate it with heaviness, with how difficult something is to lift, or with how large it looks. But these intuitions are unreliable. A small metal object can be far more massive than a large piece of foam. Feynman used such examples to show that mass is not about appearance. Nature does not care how something looks to human eyes. What matters is how that thing behaves when we interact with it physically. The moment you place an object on a balanced scale, you are no longer dealing with philosophy. You are dealing with comparison. You are asking a very precise question. Does this object balance another object? If it does, then, for the purposes of physics, they have the same mass. This idea may seem almost too simple, but it is extremely powerful. Mass becomes a number that comes from comparison, not from definition. You do not need to know what mass in order to use it accurately. You only need a reliable way to measure it. Feynman often emphasized that science advances by discovering that very different phenomena can be described by the same number. When an object balances another on a scale, and when that same object resists acceleration by a certain amount, the same number appears. That number is mass. The fact that the same quantity shows up in different experiments is not assumed, it is discovered. And this discovery is what gives mass its meaning in physics. What makes this viewpoint so important is that it removes mystery without removing wonder. Feynman was not saying that mass is trivial. He was saying that pretending to understand it at a deeper level than we actually do is dishonest. Physics is full of concepts that are defined operationally, meaning they are defined by how we measure them. Time is what clocks measure. Length is what rulers measure. Mass is what balances and resists acceleration. These are not circular definitions, they are practical ones. This approach also protects physics from empty language. Feynman was famously skeptical of explanations that sounded profound but added no predictive power. Saying, "Mass is the amount of matter in an object," sounds satisfying, but what is amount of matter? Without measurement, the phrase explains nothing. By contrast, saying, "Mass is the quantity that appears in the equations of motion and balance," may sound less poetic, but it actually works. It allows physicists to calculate, predict, and test. In this way, mass becomes a bridge between theory and experiment. When Newton wrote down his laws of motion, mass appeared as a constant connecting force and acceleration. That constant was not invented arbitrarily. It was extracted from experiments. Feynman loved pointing out that nature tells us what numbers belong in our equations, not the other way around. Mass is one of those numbers that nature insists on. Another reason Feynman rejected philosophical definitions of mass is that history shows how dangerous they can be. Before modern physics, people believed that heavier objects fall faster than lighter ones because it seemed obvious. This belief came from intuition, not measurement. It took careful experiments to show that, ignoring air resistance, all objects fall at the same rate. The intuitive idea of heaviness turned out to be misleading. Measurement corrected philosophy. By insisting that mass is what we measure, Feynman aligned himself with this experimental tradition. He was reminding students and audiences that physics is not about satisfying the mind with explanations, but about satisfying reality with tests. If a concept cannot be measured, it does not belong in physics. Mass belongs in physics precisely because it can be measured with extraordinary precision. This attitude also prepares us for later surprises. When physics moved beyond everyday objects to atoms and particles, the idea of mass became less intuitive. Particles that have no size in the classical sense still have mass. Some particles have mass, others do not. Some acquire mass through interactions. If mass had been tied to a vague philosophical idea of stuff, modern physics would have collapsed under contradiction. Because mass was already understood as a measurable quantity, physics could adapt. Feynman's emphasis on measurement also highlights the humility of science. To say, we know what mass is because we know how to measure it, is to admit that deeper questions remain open. Why do different particles have different masses? Why does mass take the values it does? These are real mysteries, and physics does not hide them behind words. It openly acknowledges them. In this sense, mass is an example of how physics progresses without pretending to final answers. We build concepts that work, test them, refine them, and sometimes replace them. The meaning of mass has evolved over time, from classical mechanics to relativity to quantum field theory. Yet throughout all these changes, one thing remains constant: mass is a number that connects experiments to equations. Feynman believed that this way of thinking trains the mind to respect reality over language. Words are tools, not truths. When words drift too far from measurement, they become illusions of understanding. By grounding mass firmly in what can be measured, physics avoids that trap. In the end, calling mass a measurable property rather than a philosophical mystery does not diminish it. It elevates it. It turns mass from a vague idea into a precise link between the human mind and the natural world. It reminds us that the universe speaks in numbers, not definitions, and that our job as physicists is to listen carefully, measure honestly, and never confuse explanation with understanding. This is the spirit in which Feynman explained mass, not as something to be admired from a distance, but as something to be tested, compared, and used, and in doing so, he showed that the true power of physics lies not in claiming to know what things really are, but in discovering how reliably they behave. Feynman's insistence that mass is a measurable property also reshapes how we think about knowledge itself. In ordinary conversation, people often believe that understanding means being able to give a verbal explanation that feels complete. But in physics, Feynman argued, understanding means being able to predict outcomes correctly. If you can predict how an object will behave when forces act on it, you understand its mass better than someone who can recite a beautiful definition but cannot calculate anything useful. This idea runs counter to how many people are educated, and that is precisely why Feynman emphasized it so strongly. Consider how mass enters physics classrooms for the first time. Students are often told definitions, then equations, then examples. Feynman preferred the opposite order. He would start with experiments pushing carts, dropping objects, balancing weights. Only after patterns emerged would the word mass appear almost as a label for something already observed. In this way, mass is not introduced as an abstract concept but as a summary of experience. The word comes last, not first. This experimental grounding explains why mass is so reliable across different contexts. Whether you are dealing with a stone, a planet, or an electron, mass appears as a number that governs behavior. The scale changes, the units change, the instruments change, but the role of mass remains consistent. Feynman found this consistency deeply satisfying, not because it answered philosophical questions, but because it demonstrated the unity of nature. A concept that works at many scales is not mysterious, it is powerful. Another important aspect of Feynman's thinking is that measurement itself is never perfect, yet mass remains meaningful. Every measurement has uncertainty. Balances wobble, instruments drift, environments interfere. Yet physicists can still talk about mass with extraordinary confidence because repeated measurements converge. This convergence is what gives mass its objectivity. It does not depend on belief, culture, or interpretation. It depends on reproducible experiment. Feynman also pointed out that different methods of measuring mass lead to the same results. You can measure mass by balancing objects. You can measure it by observing acceleration under a known force. You can infer it from orbital motion in astronomy. The fact that all these methods agree is not a logical necessity. It is an empirical fact. Nature could have behaved differently. The agreement tells us that mass is a real feature of the world, not an artifact of one particular measurement technique. This idea becomes especially important when physics enters unfamiliar territory. In particle physics, many quantities cannot be measured directly in simple ways, yet mass still shows up extracted from patterns in collisions, decays, and energy distributions. Even when the objects involved cannot be seen, touched, or isolated, mass remains measurable. This reinforces Feynman's message: physics does not require intuition, it requires consistency with experiment. By treating mass as a measurable property, Feynman also avoided the trap of false explanations. Throughout history, scientists and philosophers have proposed substances or essences to explain why objects have mass. These ideas often sounded convincing, but led nowhere experimentally. Feynman preferred explanations that reduced mystery rather than relocated it, saying, "Mass exists because of some invisible substance," explains nothing unless that substance can itself be measured and tested. This disciplined attitude becomes even more crucial when confronting modern ideas like mass generation. In contemporary physics, particles acquire mass through interactions with fields. To someone seeking philosophical comfort, this might sound like a deeper explanation. But Feynman would remind us that the real content of such theories lies in what they predict and measure. If a theory predicts the correct masses and behaviors, it is useful. If it only provides a story, it is not physics. Feynman's approach also clarifies why some questions about mass remain unanswered. Asking why mass has certain values is a legitimate scientific question, but it is not yet fully answered. Instead of hiding this ignorance behind vague language, physics openly acknowledges it. Mass is measured with extraordinary precision, yet its ultimate origin is still under investigation. This honesty is not a weakness, it is a strength. Another subtle point Feynman made is that measurement does not strip concepts of meaning, it gives them meaning. Without measurement, words drift. With measurement, words become anchored. Mass means something because it can be checked against reality. Two physicists on opposite sides of the world can agree on the mass of an object because they can perform comparable experiments. This shared agreement is the foundation of scientific knowledge. Feynman often warned students against confusing familiarity with understanding. Mass feels familiar because we experience it daily. We lift objects, feel resistance, notice effort. But familiarity can be deceptive. True understanding comes when intuition is tested against experiment and corrected when necessary. The idea that mass is simply how heavy something feels fails under scrutiny. The idea that mass is a measurable quantity survives every test. This philosophy also influences how new concepts are introduced in physics. When new quantities are proposed, physicists immediately ask, how can it be measured? If no answer exists, the concept remains speculative. Mass passed this test long ago. It earns its place in physics by being measurable in many independent ways. In the broader context of science, Feynman's treatment of mass serves as a lesson about intellectual discipline. Science progresses not by inventing explanations that sound good, but by finding relationships that hold under experiment. Mass is one of the earliest and clearest examples of such a relationship. It links force to motion, gravity to inertia, energy to matter. Ultimately, Feynman's explanation of mass as a measurable property teaches us how to think, not just what to think. It teaches skepticism toward empty words, respect for experiment, and patience with unanswered questions. Mass is not mysterious because it hides behind a secret definition. It is remarkable because it appears consistently across the laws of nature, always ready to be measured, tested, and used. In this way, mass becomes more than a physical quantity. It becomes an example of the scientific method itself. We do not begin with certainty. We begin with observation. We do not demand final explanations. We accept working descriptions that survive experiment. and we remain open to revision when new evidence appears. That is why, in Feynman's view, calling mass a measurable property is not a limitation. It is a declaration of confidence in how science works. It says that even without philosophical certainty, we can know enough to predict, to build, and to explore. And in physics, that is the highest form of understanding. When Richard Feynman explained the difference between mass and weight, he was not merely correcting a common mistake. He was exposing a deep misunderstanding about how humans relate their everyday experience to the laws of nature. In daily life, people casually use the words mass and weight as if they were the same thing. Someone says an object weighs a lot and assumes that tells the whole story. Feynman insisted that this casual language hides an important physical distinction, and understanding that distinction is essential to understanding physics itself. Weight, Feynman emphasized, is a force. It is the force with which the Earth pulls on an object. Mass, on the other hand, is not a force at all. It is a property of the object. This difference may sound technical at first, but its consequences are profound. Forces depend on circumstances. Properties belong to objects regardless of where they are. By separating these two ideas, physics frees itself from Earth-centered intuition and becomes universal. To see why this matters, imagine holding a stone in your hand. You feel its heaviness, your muscles strain slightly, and you call that sensation weight. But what you are really feeling is the force of gravity pulling the stone downward, transmitted through your hand. If you were floating far away in space, far from planets and stars, that same stone would not pull on your hand at all. Its weight would be nearly zero. Yet the stone itself would not have changed. Its mass would remain exactly the same. Feynman loved this example because it shows how misleading direct sensation can be. On Earth, gravity is so familiar and so constant that it tricks us into thinking weight is an intrinsic property. We grow up never questioning it. Everything falls downward. Everything feels heavy. But physics asks us to imagine other places, other conditions. On the Moon, the same object weighs about 1/6 as much as it does on Earth. Astronauts can lift heavy equipment with ease, not because the equipment has less mass, but because gravity is weaker. The resistance the object offers to being pushed or accelerated remains unchanged. That resistance is mass. Feynman pointed out that this distinction becomes obvious the moment you perform experiments instead of relying on intuition. Take a balance scale, the kind with two pans. Place an object on one side and standard weights on the other until the scale balances. This balance does not depend on how strong gravity is. If you took the same balance to the Moon, both sides would be pulled downward less strongly, but they would still balance in the same way. The balance compares masses, not weights. This simple device already separates the two concepts cleanly. Contrast this with a spring scale, which measures weight. A spring stretches when a force is applied. On Earth, the force of gravity stretches the spring by a certain amount. On the Moon, the same object stretches the spring much less. The reading changes because the force has changed. Feynman used such examples to show that instruments themselves reveal the difference between mass and weight if we pay attention to what they actually measure. This difference also clarifies why physics insists on precise language. When people say, "This object has a weight of 2 kilograms," they are technically wrong. Kilograms are units of mass, not weight. Weight should be measured in units of force. The fact that everyday language ignores this distinction is understandable, but physics cannot afford such sloppiness. Confusing mass and weight leads to confusion in thinking, especially when moving beyond everyday conditions. Feynman often stressed that physics is not about what feels right, but about what works everywhere. Weight is local, it depends on the gravitational field you are in. Mass is universal. It does not change when you move from Earth to the Moon to deep space. This universality is why mass plays such a central role in physical laws. The equations of motion depend on mass, not weight, because those equations must apply everywhere in the universe. Another way Feynman explained the difference is through motion. If you push an object sideways on a frictionless surface, gravity plays no role in that sideways motion, yet the object resists acceleration. A heavier object accelerates less under the same push. This resistance has nothing to do with weight. It has everything to do with mass. Even in the absence of gravity, mass reveals itself through inertia. This idea helps correct a deeply rooted misconception that gravity somehow creates mass. People sometimes think objects are heavy because gravity gives them mass. Feynman was clear that this is wrong. Gravity gives objects weight, not mass. Mass is already there. Gravity merely interacts with it. This distinction becomes critical in modern physics, where we study environments with extremely weak or extremely strong gravity. Feynman also enjoyed pointing out how the confusion between mass and weight historically slowed scientific understanding. Before careful experiments were done, it seemed obvious that heavier objects should fall faster than lighter ones. After all, they feel heavier. But experiments showed that, ignoring air resistance, all objects fall at the same rate. This surprising result only makes sense once you separate mass from weight. The gravitational force on a heavier object is greater, but its inertia is also greater in exactly the same proportion. The effects cancel, leading to the same acceleration. This cancellation is not obvious from intuition. It is revealed by measurement. Feynman saw this as a perfect example of why physics must be grounded in experiment rather than feeling. The world behaves according to precise relationships, not according to how things seem to us. By emphasizing the difference between mass and weight, Feynman was also preparing the ground for deeper ideas. Once you accept that weight depends on gravity and mass does not, you are ready to understand why gravity can be treated as a field, why free fall feels weightless, and why astronauts orbiting Earth experience apparent weightlessness, even though gravity is still acting on them. None of these ideas make sense if mass and weight are confused. In orbit, for example, astronauts float freely. People often say there is no gravity in space, but this is false. Gravity is still present and still pulling on them. What is missing is weight, because there is no supporting force pushing back against gravity. This subtle distinction becomes clear only when mass and weight are properly separated. Feynman's treatment of mass versus weight also reflects his broader philosophy of teaching. He wanted students to unlearn misleading intuitions and replace them with experimentally grounded understanding. He was not interested in memorizing definitions, but in seeing how concepts behave across different situations. Mass stays the same, weight changes. That simple statement, once fully understood, unlocks a great deal of physics. Ultimately, by explaining the difference between mass and weight, Feynman showed how physics transforms everyday experience into universal law. What feels like heaviness becomes a force. What feels like resistance becomes a property. And once these are separated, the universe becomes clearer, more consistent, and far less confusing. This clarity is not achieved by redefining words, but by respecting what experiments tell us about how nature actually works. Feynman also used the distinction between mass and weight to teach an even deeper lesson, that physics often requires us to let go of Earth-based thinking. Humans evolved under gravity, so our language, intuition, and instincts are shaped by it. We feel weight every moment of our lives. Because of this, weight feels fundamental, while mass feels abstract. Feynman deliberately reversed this perspective. In physics, mass is fundamental, weight is incidental. This reversal is uncomfortable at first, but it is necessary if we want to understand the universe beyond our immediate surroundings. One of the most striking demonstrations of this idea comes from situations where gravity is changing or absent. In an accelerating elevator, for example, your weight changes even though your mass does not. If the elevator accelerates upward, you feel heavier. If it accelerates downward, you feel lighter. In free fall, you feel weightless. None of these sensations mean that your mass is changing. They only reflect changes in forces acting on you. Feynman loved such examples because they show how unreliable sensation is as a guide to physical reality. This realization leads to a profound shift in thinking. Weight is not something an object has by itself. Weight is something that happens to an object when gravity acts on it, and when another force prevents it from falling freely. When you stand on the ground pushes up on you while gravity pulls down. That upward push is what you interpret as weight. Remove the ground and the sensation disappears. Mass, however, remains even when no force is acting at all. Feynman often emphasized that once you understand this, many confusing ideas suddenly become simple. Astronauts floating inside a spacecraft are not weightless because gravity is gone. They are weightless because the spacecraft, and everything inside are all falling together under gravity. There is no supporting force to create the sensation of weight. Their mass is still there, fully intact, governing how they move when they push off a wall or throw an object across the cabin. This clarity becomes especially important in engineering and space science. When engineers calculate how much fuel is needed to change a spacecraft's trajectory, they use mass, not weight. Gravity may vary from place to place, but inertia does not. If mass and weight were confused, space travel would be impossible to calculate reliably. Feynman stressed that physics must be formulated in terms that work everywhere, not just on Earth. Another subtle but crucial point Feynman made is that mass is what allows objects to have momentum. Momentum depends on mass and velocity. Weight does not enter the definition at all. An object moving through empty space carries momentum, even if it weighs nothing in that environment. Collisions, explosions, and recoil all depend on mass, not weight. This again shows that mass is the deeper concept. Feynman also used the mass-weight distinction to expose sloppy thinking in everyday science communication. Phrases like zero gravity or losing mass in space are common but misleading. Gravity may be weaker in some places, but it is rarely zero. Objects do not lose mass when they leave Earth, they lose weight. These may sound like small linguistic issues, but Feynman believed they mattered because language shapes thought. If the language is wrong, the thinking that follows will also be wrong. By insisting on precision, Feynman was not being pedantic, he was protecting understanding. When students confuse mass and weight, they often struggle later with more advanced ideas like energy, momentum, and relativity. The confusion compounds. But when the distinction is clear from the beginning, later concepts fit together naturally. This distinction also prepares the mind for Einstein's insights. In general relativity, gravity is not treated as a traditional force in the same way as others. The equivalence between gravitational effects and acceleration becomes central. The fact that weight can disappear in free fall while mass remains is a key clue that gravity behaves differently from other forces. Feynman did not dive deeply into relativity when explaining mass and weight, but he made sure the groundwork was laid. There is also a philosophical lesson hidden in this discussion, though Feynman rarely framed it that way. Humans tend to think that what they feel must be fundamental. Physics repeatedly shows that this is not true. We feel heat, but temperature is a statistical property. We feel heaviness, but weight is a force dependent on environment. Mass, which we do not directly feel, turns out to be more fundamental than either. Physics trains us to distrust feeling and trust measurement. Feynman's teaching style made this lesson memorable. He did not simply state facts, he challenged assumptions. He invited listeners to imagine unfamiliar situations, to test their intuitions and watch them fail. In doing so, he showed that learning physics is not about adding new facts, but about reorganizing how you think. Ultimately, the difference between mass and weight is not just a technical distinction. It is an example of how physics strips away local, human-centered perspectives and replaces them with universal ones. Weight ties you to a planet. Mass connects you to the laws of motion that govern the entire cosmos. By the time Feynman finished explaining this idea, mass no longer seemed abstract. It seemed solid, reliable, and universal. Weight, once thought obvious, became conditional and secondary. This inversion is exactly what good physics does. It takes what seems obvious and questions it, and it takes what seems abstract and grounds it in experiment. In this way, the simple act of distinguishing mass from weight becomes a gateway to scientific thinking itself. It teaches careful use of language, respect for experiment, and willingness to abandon intuition when it conflicts with evidence. For Feynman, this was not just about teaching physics, it was about teaching how to think clearly about the world. And that is why, in his explanation, the difference between mass and weight is far more than a classroom correction. It is a lesson in humility before nature, reminding us that the universe does not organize itself around human sensation, but around laws that reveal themselves only when we measure, compare, and think with discipline. When Richard Feynman explained inertial mass, he focused on one of the most direct and revealing ways mass shows itself in nature. Resistance to change in motion. This idea does not depend on gravity, weight, or location. It appears the moment you try to push, pull, or accelerate anything. Inertial mass is not about how heavy something feels, but about how stubborn it is when you try to make it move differently. For Feynman, this was one of the clearest and most honest ways to understand what mass actually does. Imagine an object resting on a smooth, frictionless surface. If you push it gently, it begins to move. Push harder, and it accelerates faster. Now repeat the experiment with a much more massive object. Apply the same push, and you immediately notice a difference. The heavier object accelerates less. Nothing mysterious is happening. The object is simply resisting the change in its motion. That resistance is inertia, and inertial mass is the numerical measure of how strong that resistance is. Feynman emphasized that this resistance exists even in the complete absence of gravity. You could perform the same experiment in deep space, far from any planet or star, and the result would be the same. An object with greater mass would still resist acceleration more strongly than one with less mass. This shows that inertial mass is a fundamental property of matter, independent of gravitational effects. Gravity is not required for mass to matter. This point is crucial because it separates mass from many everyday intuitions. People often associate mass with heaviness, and heaviness with gravity. But inertial mass has nothing to do with falling or being pulled downward. It reveals itself through motion itself. Whether you are pushing a shopping cart, accelerating a car, or firing a rocket engine in space, inertial mass is always present, quietly determining how much acceleration results from a given force. Feynman often returned to Newton's second law, not as a definition, but as a relationship discovered through experiment. Force is proportional to acceleration, and the constant of proportionality is mass. This equation is not telling us what mass is, in some philosophical sense. It is telling us how mass behaves. If you double the force on an object, you double its acceleration. If you double the mass while keeping the force the same, you have the acceleration. These relationships are measurable and repeatable, and that is what gives inertial mass its meaning. What fascinated Feynman was not the equation itself, but the fact that nature behaves so consistently. The same mass that resists acceleration sideways also resists acceleration upward, downward, forward, or backward. Direction does not matter. Speed does not matter as long as we are not approaching relativistic speeds. Mass acts as a universal measure of resistance to acceleration. This universality is not obvious, it is discovered. In everyday life, friction and gravity often hide inertial mass from view. When you push a heavy object across the floor, friction resists motion, making it difficult to separate inertia from other forces. Feynman encouraged stripping problems down to their essentials, imagining idealized situations where friction is removed. In these simplified scenarios, inertial mass stands out clearly as the factor controlling acceleration. This idea also explains why objects in motion behave the way they do. Once an object is moving at a constant velocity, it does not require force to keep moving. It requires force only to change its motion. This is another aspect of inertia. Mass is not a measure of how much force is needed to keep something moving, but how much force is needed to change its state of motion. This insight overturned centuries of incorrect thinking and became one of the foundations of classical physics. Feynman liked to stress that inertial mass is revealed through interaction. You do not observe mass in isolation. You observe it when forces act. A force without mass produces infinite acceleration, which does not happen in nature. Mass without force produces no change, which is equally uninformative. Meaning arises when the two meet. This relational view fits perfectly with Feynman's broader philosophy. Physics is about relationships, not essences. As experiments became more precise, physicists discovered that inertial mass is incredibly consistent. No matter how you measure it, the same value appears. You can measure it through acceleration experiments, collision experiments, or oscillatory motion. The results agree. This agreement is not guaranteed by logic. It is a fact about the universe. Feynman found this deeply satisfying because it shows that mass is not an artifact of a particular experimental setup. Inertial mass also plays a central role in conservation laws. Momentum depends on mass and velocity. Energy depends on mass and motion. When objects collide, exchange momentum, or recoil, inertial mass determines the outcome. These processes do not depend on gravity. They occur in particle accelerators, in interstellar space, and in everyday mechanical systems. Everywhere, mass governs how motion changes. Feynman often used collisions to illustrate inertial mass. When two objects collide, the more massive one changes its velocity less than the less massive one. This behavior is immediately observable, whether in billiard balls, cars, or subatomic particles. Again, no gravity is required. The collision itself reveals the masses involved. This brings us to an important conceptual point. Inertial mass is not something you see, it is something you infer. You infer it from how objects respond to forces. This is why Feynman resisted attempts to reduce mass to some underlying substance or picture. The power of mass lies not in visual imagery, but in predictive ability. If you know the mass, you can predict motion. That is enough. As physics advanced into the microscopic world, inertial mass retained its importance. Electrons, protons, and other particles all have inertial mass. They resist acceleration just like everyday objects do, though on vastly different scales. In particle accelerators, enormous forces are applied to particles, yet their acceleration is still limited by their mass. This continuity across scales is one of the great triumphs of physics. Feynman also noted that inertial mass is what makes reference frames meaningful. When you accelerate, you feel forces that depend on your mass. These inertial forces reveal acceleration even in the absence of external reference points. Again, mass plays a central role in how motion is experienced and described. By focusing on inertial mass, Feynman highlighted a form of mass that is stripped of metaphor and intuition. It is not about heaviness, size, or substance. It is about response. How much does an object resist being pushed? How much does it resist being sped up, slowed down, or redirected? The answer to these questions is inertial mass. In this way, inertial mass becomes one of the most honest faces of mass. It does not depend on where you are. It does not depend on gravity. It does not depend on how something looks or feels. It depends only on how nature responds when you try to change motion. For Feynman, this made inertial mass not only fundamental, but beautifully simple. And yet, despite this simplicity, inertial mass raises deep questions. Why do different objects have different inertial masses? Why does mass take the values it does? Physics can measure inertial mass with incredible precision, but it does not yet fully explain its origin. Feynman was comfortable with this. He believed that admitting ignorance where it exists is a sign of strength, not weakness. Thus, inertial mass stands as a perfect example of Feynman's approach to physics. It is defined by experiment, revealed through behavior, and used to predict the world with astonishing accuracy. It does not need philosophical decoration. Its meaning lies in what it does. Feynman's discussion of inertial mass did not end with simple pushes and accelerations. He used this idea as a doorway into a deeper understanding of how motion itself is described in physics. Inertial mass is inseparable from the concept of reference frames, because it determines how objects respond when those frames accelerate. This is one of the reasons inertial mass, appears so naturally in the laws of motion. It is tied to how we define motion in the first place. When you sit in a car that suddenly accelerates forward, you feel yourself pressed back into the seat. Nothing is actually pulling you backward. What you feel is your own inertia resisting the change in motion. Your body wants to remain in its original state of motion, and the seat must push you forward to make you accelerate along with the car. The strength of that push depends on your inertial mass. This everyday experience is a direct demonstration of inertial mass at work, even though people rarely think of it in those terms. Feynman emphasized that these inertial effects are not illusions. They are real forces that arise when describing motion from an accelerating frame of reference. The key point is that mass determines how strongly these effects appear. A more massive object experiences larger inertial forces under the same acceleration. This again shows that inertial mass is deeply woven into the structure of mechanics, not just an add-on parameter. This understanding also explains why inertial mass is central to engineering and technology. When designing vehicles, machines, or structures, engineers must account for how mass resists acceleration. Rapid starts, stops, and turns all involve inertial forces. The greater the mass, the greater the forces involved, and the stronger the materials must be. Gravity may change from place to place, but inertia does not. That is why mass, not weight, is the key quantity in these calculations. Feynman also highlighted how inertial mass governs energy exchange. The kinetic energy of an object depends on its mass and velocity. For a given speed, a more massive object carries more energy. This is not because it is made of more stuff, in some vague sense, but because changing its motion required more work. Energy, in this context, is a record of how much effort was needed to overcome inertia. This perspective ties mass, motion, and energy together in a very concrete way. In collisions, inertial mass determines how motion is redistributed. When two objects collide, the changes in their velocities depend on their masses. A light object bouncing off a heavy one recoils dramatically, while the heavy object barely changes its motion. These outcomes are not arbitrary. They follow directly from the way inertial mass enters the conservation of momentum. Feynman often used such examples to show that mass is not an abstract number, it is the key to predicting real events. As physics moved into relativistic regimes, inertial mass took on new subtleties, but its core role remained. At speeds close to the speed of light, the relationship between force and acceleration becomes more complex. Yet even here, mass continues to measure resistance to acceleration, though in a way that depends on energy and velocity. Feynman acknowledged these complications without losing sight of the underlying principle. Mass governs how difficult it is to change motion. This continuity between classical and modern physics was important to Feynman. He wanted students to see that new theories do not discard old concepts entirely, they refine them. Inertial mass remains meaningful, even as our understanding of motion deepens. The same experimental spirit applies measure how systems respond to forces and extract the quantities that describe that response. Feynman also used inertial mass to illustrate the power of abstraction. By focusing on resistance to acceleration, physics ignores irrelevant details like shape, color, or composition. Two objects made of completely different materials can have the same inertial mass if they respond the same way to applied forces. This abstraction allows physics to uncover simple laws beneath the complexity of the visible world. Another subtle point Feynman emphasized is that inertial mass is additive. Combine two objects, and their combined inertial mass is the sum of their individual masses. This property is not trivial. It had to be tested and confirmed. It allows us to treat complex systems as collections of simpler parts, each contributing to the whole. Without this additivity, much of classical mechanics would be impossible. Inertial mass also plays a role in stability. Systems with larger mass tend to change more slowly under the same influences. This inertia gives them a kind of persistence. Planets follow stable orbits. Large structures resist sudden motion. These behaviors are not mystical, They are consequences of mass interacting with forces over time. Feynman appreciated how such simple principles could explain phenomena on vastly different scales. Despite all this, Feynman never suggested that inertial mass is fully understood. He was careful to distinguish between knowing how something behaves and knowing why it exists. Physics knows how inertial mass works. It does not yet know why the universe assigns particular masses to particular particles. This open question remains at the frontier of science. What mattered to Feynman was that this ignorance did not prevent progress. By accepting inertial mass as an experimentally established quantity, physics could build reliable theories, design technologies, and explore the cosmos. Waiting for ultimate explanations would have stalled discovery. In the end, inertial mass stands as a testament to the pragmatic power of physics. It is a concept grounded in experiment, validated across countless situations, and essential to understanding motion. Feynman's explanation strips it of unnecessary mystery while preserving its depth. Mass resists change. That simple fact, measured carefully and applied consistently, is enough to describe an astonishing range of natural phenomena. Through inertial mass, Feynman taught not just a concept, but a way of seeing the world. Look at what changes. Look at what resists change. Measure it. Trust the measurement. And let nature, not intuition, tell you how the universe works. When Richard Feynman turned to gravitational mass, he focused on one of the most surprising and quietly profound facts in all of physics. The mass that determines how strongly an object responds to gravity is exactly the same mass that determines how strongly it resists acceleration. This equality is not something that logic demands. It is not something we could have predicted in advance. It is something nature reveals through experiment, and Feynman considered this one of the most beautiful examples of how the universe behaves according to simple patterns that are not obvious from everyday thinking. Gravitational mass appears when an object is placed in a gravitational field. It determines how strong the gravitational force on that object will be. If two objects have different gravitational masses, gravity pulls on them with different strengths. At first glance, this seems straightforward and intuitive. A more massive object experiences a stronger gravitational pull. But what makes this remarkable is what happens next. The same object that feels a stronger pull also resists motion more strongly in exactly the same proportion. Feynman emphasized that this exact matching is extraordinary. The gravitational force on an object increases with its gravitational mass, but the object's resistance to acceleration increases with its inertial mass. If these two masses were even slightly different, objects of different composition would fall at different rates, but experiments show that they do not. Ignoring air resistance, all objects fall with the same acceleration in a given gravitational field. This is not a coincidence. It is a precise and universal result. Historically, this fact puzzled physicists for centuries. Galileo's experiments hinted at it. Newton's laws incorporated it without explaining it. By Feynman's time, the equality had been tested with extraordinary precision, and no deviation had ever been found. Yet no simple explanation existed within classical physics. Feynman loved this situation because it showed science at its most honest, a deep truth confirmed by experiment, even though its ultimate reason remained mysterious. This equality means that gravity treats all objects the same way, regardless of their internal composition. A rock, a piece of wood, and a block of metal all accelerate identically in free fall. Gravity does not care what something is made of. It only sees mass, and it sees inertial and gravitational mass as one and the same. Feynman stressed that this universality is what allows gravity to be described so cleanly in physical laws. The consequences of this fact are enormous. Because inertial and gravitational mass are equal, gravitational acceleration does not depend on the mass of the falling object. This leads directly to the idea of free fall as a universal motion. In free fall, objects are not being pushed or pulled in any complicated way. They are simply following the natural motion dictated by gravity. This insight was essential for Einstein's development of general relativity. Although Feynman did not always dive deeply into relativity when explaining mass, he made it clear that the equality of inertial and gravitational mass is the key clue behind Einstein's theory. If gravity affects all objects in exactly the same way, then gravity is not just another force like friction or electricity. It is something more subtle. It can be understood as a property of space and time themselves, rather than as a force acting within space. Feynman liked to point out that this profound conclusion rests on a very simple experimental fact. Drop different objects and watch how they fall. Perform the experiment carefully enough, and you see that they fall together. From this humble observation comes an entirely new way of thinking about gravity and the structure of the universe. This is exactly the kind of result Feynman admired, a deep theory rooted in simple, repeatable experiments. He also emphasized that the equality of masses is not something we define by choice. We do not say inertial mass equals gravitational mass because it is convenient. We say it because experiments force us to. Physics does not get to decide how nature behaves. It only gets to describe what nature actually does. This perspective also reinforces Feynman's broader lesson about humility in science. Even when a fact is extraordinarily well confirmed, its deeper explanation may remain unknown. We know that inertial and gravitational mass are equal. We know how to use this fact with incredible precision, but asking why they are equal leads to questions that push the boundaries of current knowledge. Feynman saw no problem with this. For him, acknowledging mystery was part of respecting reality. In the end, gravitational mass serves as a bridge between motion and gravity, between everyday experience and the deepest theories of physics. It shows that nature sometimes repeats the same number in places where we might not expect it. That repetition is not dull, it is astonishing. It hints at an underlying unity in the laws of the universe. Through this discussion, Feynman demonstrated how a single experimental fact can reshape our understanding of reality. The equality of inertial and gravitational mass is not just a technical detail. It is a window into how gravity works, why objects fall the way they do, and how space and time themselves might be structured. And it all begins with a simple idea. The mass that resists motion is the same mass that responds to gravity, every time, everywhere. When Richard Feynman discussed mass at the atomic and subatomic level, he carefully dismantled one of the most persistent intuitions people have about matter, the idea that mass is simply the result of solid substance packed into space. At the scale of everyday objects, this intuition seems reasonable. Heavier objects often look denser, more compact, more filled. But when physics looks deeper, this picture collapses, and mass reveals itself as something far more subtle and surprising. Atoms, which make up all ordinary matter, are mostly empty space. If an atom were enlarged to the size of a stadium, its nucleus would be a tiny speck at the center, and the electrons would be moving in regions far away from it. Yet, despite this emptiness, atoms have mass. Feynman emphasized that this immediately tells us mass cannot simply be about how much space something fills. Something almost entirely empty can still have a well-defined and measurable mass. At first glance, one might think that atomic mass is just the sum of the masses of protons, neutrons, and electrons. To some extent, this is true, but even this explanation turns out to be incomplete. Protons and neutrons themselves are not solid, indivisible objects. They are made of quarks, bound together by powerful forces. The surprising result of modern physics is that most of the mass of protons and neutrons does not come from the masses of the quarks alone. Feynman highlighted that energy plays a central role here. The quarks inside protons and neutrons are in constant motion, held together by strong interactions. According to the laws of physics, energy contributes to mass. The motion of quarks and the energy stored in the forces between them account for most of the mass of ordinary matter. In other words, much of what we call mass is actually energy in a highly confined and dynamic form. This idea challenges everyday intuition. We are used to thinking of energy as something abstract, like heat or motion, and mass as something solid. At the atomic level, this distinction becomes blurred. Mass is not a static substance, it is a measure of how much energy is bound into a system. Feynman took great care to explain this without mysticism. He did not say mass turns into energy in a magical way. He said that mass and energy are two ways of describing the same physical reality. Electrons add another layer of subtlety. Electrons have mass, but they are not little solid balls orbiting a nucleus like planets. They behave according to quantum rules, appearing as probability clouds rather than definite objects with precise positions. Yet their mass is just as real and measurable as that of larger objects. This shows that mass does not require classical solidity. It applies equally to quantum entities. Feynman often stressed that physics does not ask what particles look like in a visual sense. It asks how they behave. An electron's mass is known because we can measure how it responds to forces, how it curves in magnetic fields, and how it accelerates. The same experimental logic applies at all scales. Mass is defined by behavior, not by appearance. At the subatomic level, particles also differ dramatically in mass. Some are heavy, some are light, and some have no mass at all. These differences are not explained by size or shape. They are fundamental properties that must be measured and accepted. Feynman found this both humbling and exciting. Nature does not arrange itself according to human expectations. It simply is the way it is, and physics must adapt. Another important point Feynman made is that mass at the atomic scale is not always conserved in simple ways. When atoms bind together to form molecules or nuclei, the total mass of the system can be slightly less than the sum of the masses of its parts. The missing mass has been released as energy. This effect is small in chemical reactions and much larger in nuclear reactions, but the principle is the same. Mass is not lost, it is transformed. This realization has enormous consequences. It explains why nuclear reactions release such tremendous amounts of energy. It also reinforces the idea that mass is not a fixed substance but a dynamic quantity tied to energy and interaction. Feynman used this to show how classical ideas must be expanded, not discarded, when physics moves to new scales. Despite all these complexities, the concept of mass remains remarkably consistent. Whether dealing with atoms, particles, or planets, mass still measures resistance to acceleration and response to gravity. The underlying mechanisms may differ, but the observable behavior is unified. This unity is one of the great achievements of physics. Feynman's treatment of mass at the atomic and subatomic level shows how deeply experimental thinking shapes understanding. Instead of clinging to outdated pictures, physics follows where measurement leads. Mass turns out to be less about stuff and more about energy, motion, and interaction. This does not make the world less real. It makes it more interesting. In the end, by exploring mass at these tiny scales, Feynman revealed a universe that is far richer than common sense suggests. The solid objects of everyday life emerge from a restless, energetic, and mostly empty atomic world. Mass is the thread that connects these levels, linking the familiar to the invisible through precise and reliable measurement. When Richard Feynman spoke about the connection between mass and energy, he was careful to remove the aura of mystery that often surrounds the famous equation linking the two. Rather than presenting it as a magical statement, he treated it as a precise summary of experimental facts. The idea that mass and energy are deeply related did not arise from philosophical speculation. It emerged from the need to make the laws of physics consistent across different frames of motion. The relationship between mass and energy becomes clear when one considers how energy behaves. Energy can appear in many forms: motion, heat, radiation, or stored interaction. Feynman emphasized that energy is not a substance but a bookkeeping tool, a way of keeping track of changes in a system. Mass, surprisingly, turns out to be part of that bookkeeping. A system with more energy has more mass, and a system that loses energy loses mass, even if the change is extremely small. This idea is easiest to see in situations where large amounts of energy are involved. In nuclear reactions, for example, a tiny amount of mass disappears and an enormous amount of energy is released. Feynman stressed that nothing mystical is happening here. The total amount of mass energy is conserved. What changes is the form in which it appears. The mass of the final products is slightly less than the mass of the initial components, and the difference shows up as released energy. He also explained that this connection works in the opposite direction. If you add energy to a system, its mass increases. Heat an object, and its mass becomes slightly larger, even though the increase is far too small to detect with ordinary instruments. Accelerate particles to high speeds, and their total energy increases, along with their effective mass. These effects have been measured and confirmed, not guessed. Feynman was particularly careful to clarify common misunderstandings. The equation connecting mass and energy does not mean that mass is made of energy, in a simple or literal sense. Nor does it mean that energy is always easily converted into mass. The equation tells us that mass is one form in which energy can appear. Whether or not conversion occurs depends on the physical processes involved. Physics is precise about conditions, not vague about possibilities. This connection also reshapes how we think about rest and motion. Even an object at rest contains energy simply by virtue of having mass. That energy is not kinetic energy, it is intrinsic to the object. Feynman pointed out that this rest energy is not directly observable in everyday situations, but it becomes crucial in high-energy physics and cosmology. Without accounting for it, the behavior of particles and stars cannot be understood correctly. At a deeper level, the mass-energy relationship reflects the structure of space and time. As objects move faster, approaching the speed of light, energy and momentum must be treated in a unified way. Mass appears as part of this unified description. Feynman did not present this as an abstract mathematical trick. He emphasized that it was forced upon physicists by experimental results. Nature demanded a new framework, and mass-energy equivalence was part of that framework. This idea also explains why some particles can exist without mass. Particles that travel at the speed of light, such as photons, carry energy and momentum but no rest mass. Their behavior fits perfectly within the mass-energy framework. Feynman liked pointing out that this consistency across different kinds of particles is a strong sign that the theory captures something real about the universe. Another important implication is that mass is not an absolute measure of how much matter exists. Two systems can contain the same number of particles and yet have different masses if their internal energies differ. Binding energy, motion, and interaction all contribute. This perspective dissolves older notions of mass as a fixed, unchanging substance. Despite its revolutionary implications, Feynman presented the mass-energy connection with restraint. He resisted dramatic language. For him, the true wonder lay in how accurately the relationship worked, not in how shocking it sounded. Physics, he believed, should inspire awe through precision, not exaggeration. In the end, the connection between mass and energy completes the picture of mass that begins with inertia and gravity. Mass is not an isolated concept. It is woven into motion, force, and energy. Understanding this connection does not make mass mysterious, it makes it coherent. It shows that mass is part of a larger, elegant structure that governs how the universe behaves at every scale. Through this explanation, Feynman demonstrated how physics progresses by unifying ideas that once seemed separate. Mass and energy, once thought to be entirely different, turn out to be deeply related aspects of the same underlying reality. This insight does not replace measurement or experiment, it strengthens them. It allows physicists to predict new phenomena and understand old ones with greater clarity, staying true to the experimental spirit that defines science. When Richard Feynman spoke about why mass is defined by experiment rather than by definition, he was pointing to the very heart of scientific thinking. In everyday life, people often believe that once you give something a definition, you have explained it. Feynman rejected this idea completely. For him, definitions are labels, not understanding. True understanding in physics comes from discovering how quantities behave and how reliably they can be measured. Mass is a perfect example of this philosophy. There is no single sentence that captures what mass really is in a final way. Any verbal definition eventually circles back to other undefined words. Instead of chasing such circular explanations, physics asks a different question: how do we determine mass in practice? Once that question is answered, mass becomes a usable and meaningful concept, even if deeper questions remain open. Feynman emphasized that experiments come first and definitions come later. Physicists did not sit down and invent mass as an abstract idea. They noticed regularities in how objects moved, collided, and responded to forces. They discovered that a single number could describe an object's resistance to acceleration, its behavior in collisions, and its response to gravity. That number was named mass. The name followed the discovery, not the other way around. This approach explains why mass appears in so many different laws of physics. It shows up in mechanics, gravity, energy, and momentum, not because someone defined it that way, but because experiments demanded it. Each time physicists tested a new situation, the same quantity appeared again. This repetition is what gives mass its authority. It earns its place in physics by being unavoidable. Feynman also pointed out that experimental definitions protect science from illusion. Words can be misleading. They can give the impression of understanding without delivering any predictive power. An experiment cannot do that. An experiment either works or it does not. If a quantity cannot be tied to measurement, it cannot be tested. And if it cannot be tested, it does not belong in physics. Mass belongs because it is measurable in many independent ways. Another important lesson is that experimental definitions allow concepts to evolve. As physics advances, our understanding deepens, and theories change, yet mass remains meaningful because it is anchored to measurement. Classical mechanics, relativity, and quantum theory all use the concept of mass, even though they interpret it differently. The continuity is provided by experiment, not by words. Feynman believed this flexibility was one of the great strengths of science. A rigid definition would break when new discoveries arrived. An experimental concept adapts. When new phenomena appear, physicists check how the measured quantity behaves and adjust their theories accordingly. Mass has survived this process remarkably well. He also stressed that defining mass experimentally does not make it arbitrary. On the contrary, it makes it objective. Anyone, anywhere, using the same experimental procedures, will obtain the same results within measurement uncertainty. This universality is what allows physics to be a global enterprise. Mass does not depend on culture, language, or philosophy. It depends on nature. Feynman often used this point to caution against overconfidence. Even when a concept works extremely well, science does not claim to have exhausted its meaning. There may be deeper explanations waiting to be discovered. The experimental definition keeps the door open. It says, "This is what we know so far, and this is how we know it." That honesty is central to scientific progress. Another consequence of this view is that some questions, while interesting, are not immediately scientific. Asking, "What is mass really?" may express curiosity, but without a way to test the answer, it remains philosophical. Physics does not dismiss such questions, it simply sets them aside until they can be connected to experiment. Feynman was comfortable with this separation. He believed it kept science clear and productive. By grounding mass in experiment, Feynman also showed how science builds trust. When predictions based on mass work again and again, confidence grows. Bridges stand, machines function, spacecraft reach their destinations. None of this depends on a perfect verbal definition. It depends on reliable measurement and consistent laws. In the end, Feynman's insistence on experimental definition is not a limitation, but a celebration of how science works. It acknowledges that human language is imperfect, while nature is precise. By listening to nature through experiment, physics constructs concepts that are robust, adaptable, and powerful. Mass, defined this way, becomes more than a term in an equation. It becomes an example of scientific humility and strength combined. We may not know why mass has the values it does, or why it appears exactly where it does in the laws of nature. But we know how to measure it, how to use it, and how to test ideas about it. And for Feynman, that was not a weakness of science. It was its greatest achievement.